Alright, so I apologize about not uploading on Monday. If you look at the dates of the videos and notice that I wasn't consistent with that, my bad. I was setting up for the calculus series that's coming up because this playlist is about to end. Thankfully. I really do not enjoy showing how to do this. I mean, I don't have any issue showing you guys, it's just that I'd rather go on to more things, explain why calculus the way it is and all sorts of things. Differentials, wow, I just forgot calculus. But, I've been setting up that playlist and it will be up soon, so don't worry. But now, let's just get on to the video. For today, I wanted to talk about manipulating functions. So, manipulating, that's, from the way I'm saying it, is that, here, let's say this. If you can shift a function that's graphed, like to the left or right, or up and down, how would we endeavor to do such a thing? Alright. So first, let's talk about shifts. There's a horizontal shift, and there's a vertical shift. A horizontal shift, if you don't know what horizontal means, it's this direction. It's on the x-axis. A vertical shift, you move the function upwards or downwards. You'd be able to know how many units that you'd actually move a function by these little things that you can do to actually, change the way they look here. An example of a horizontal shift is something like x minus 1 squared. Now, let's compare it to the graph of x squared. So x squared, here, first, if you want to know what type of shift it is, if you don't know off the bat, if it's a horizontal or vertical shift, just know this. A horizontal shift will always be attached to the function inside of it. But I'll show you the vertical shift and I'll compare it. But you have to look for the zeros. So our 0 for x squared is at 0. But our 0 for this one is at 1. So it horizontally shifted right. 1 unit. Just remember that if you need to describe it. Now let's talk about a vertical shift. This is where I'll actually explain how it compares. So, a graph of x squared minus 1, you'd actually be able to know if how many zeros there are based on what this looks like. Because if you have it like this, then you can follow this thing called the fundamental theorem of algebra. So we have 2 zeros. If there are 2 zeros, then you know that it's coming in from the bottom. Although this should have 2 zeros, so where would that come from? Well, that's going to go into a little complex thing that I'll talk into the later video. But this graph, since it has 2 zeros, you know it's coming in from the bottom, so it would look like this. So, similar to the x squared graph, but down here. It's a really simple concept. Just know how this stuff works. You can also do this to logarithmic graphs. Okay, so first of all, just remember, if you're, let's see. No, I haven't started talking about composite functions. Here, I'll remember to talk about the other idea, but basically, if you want to know if it's a horizontal or vertical, it is either attached to it or not attached to it. Because think of it as a linear equation, even though it isn't linear. Because in a linear equation, it will have this, but it's manipulated by the b in y equals mx plus b. So it will either shift up or down based on that. And it will change direction based on what the x is. And here's a little trick to knowing that, actually it's not really a trick, I'm just going to tell you. If it's negative x squared, it goes down. That's it. That's the entire thing. Now, I'm going to show you other things you can do with logarithmic graphs and all that. So, if you have, let's see, log of x as one of the functions with base 10, as you should remember from the other video, then log of x minus 1 does exist. But the thing is that x cannot equal 1, and it cannot equal anything less than 1. So less than or equal to. So it would become asymptotic at 1. So if you have the graph of log of x... Okay, I think I butchered that. Then it would shift over here, and it would become at... Oh my goodness! Quiet! Shut up! Okay. Oh my goodness. All I want to do is just show you guys how to do this. Oh. I'm gonna have to eat them. Okay, I'm just gonna I can't think when those dogs are yapping. I don't even like those dogs. Oh. Okay, whatever. So it becomes asymptotic at 1. So you know that you could shift it that way, although you know that it's going to be a horizontal shift because it's inside what's actually changing. It's manipulated with it. And you know that if it's log of x plus 1, then it would actually raise up to around here. I am messing up these graphs. I cannot think. Let's see, what else? And it should be evident with quotient functions. Crap, I lost my train of thought. Okay, so with quotient functions, you know that it's going to change based on the fact that if you have 1 over x and then 1 over x minus 1, just find where it doesn't exist. Because it's always not existing at 1 divided by 0. And then 1 over x minus 1, x cannot equal 1, alright? Now let's talk about compressions and stretches. Actually, one thing before we go on, look at the zeros every single time. You'll be able to understand if it's not a compression, a horizontal shift or a vertical shift. Always look for it, because if it's a vertical shift, then you know that it will either create 2 zeros, unless the original function already had it, or it will remove all zeros, because x squared plus 1 does not have any zeros that are in the real plane, which I will talk about the complex plane soon. Just give me a moment. See, I have 31 minutes left on this. Alright, so a compression. You'll be able to know how a compression looks based off little examples. Am I running out of marker? Oh no. So we have a graph of x squared over here. I use x squared a lot. I think I should change up how I do that. Someone pulled up. I'm just going to end it here, but I will come back to this. Alright, so let's get back to it. So, let's say that we have a number bigger than 1. We'll just call it A. multiplied it by the example of x squared. So a is greater than 1. And it has to be greater than 1 because a equaling 1 would just be that graph. That wouldn't make any sense. And let's pull out a b. B being lesser than 1. The first one, ax squared, a being greater than 1, is what we call a compression. A compression will do this. It will start making it thinner and thinner, and it will start covering this area. And you're able to do it without having to calculate everything because, well, if you know a number is multiplied by some bigger number, like let's say 2 times, let's plug in a 2, and then you multiply it by 2, that's going to give you 8. So at 2, it's going to increase all the way up here, and it's going to be, well, it's going to grow a lot faster than the x squared graph. Because, well, look at it. 2 would probably be right around here, and 2 on the arbitrary value of just plugging in 2 for a would give you a bigger number. But b being lesser than 1 will actually do this. It will begin going down here further and further, and it will basically approach 0. And you should be able to understand that, because let's say you plug in half, and you plug in a 1. Then if you plug in 1, you get half. That doesn't equal 1, that's going to be down here. And that's how compressions and stretches work. So this one is a stretch, this one is a compression. Do you understand that? Well, I can't hear you. I just thought that it would feel good to say that. And you have to remember that even if there's a compression or a stretch, it's still going to manipulate the 0. Because let's say there's a vertical shift on this one, along with a compression. Because it'll be like 3x squared minus 1. Then what do? Because that'll basically have to be root 3 over 3. That would be the roots. So we know that these 4 things manipulate zeros. But let's talk about how to actually find those zeros. Because it's not going to stay consistent. You won't be able to do it in your head all the time. So let's start off. By the way, I'm not going to prove this. No, you can look at other people's videos for that. All you need to know is just a single equation. Negative b plus or minus the square root of b squared minus 4ac divided by 2a. You will always find your zeros with that, but we should probably understand where this is coming from. This only deals with degree 2 equations. So it will have an a, and then a b, and then a c. And from what we know from the fundamental theorem of algebra, that you will find a 0 for every number, every natural number that's in the degree. Okay? Because how do you find 1.5? Like, that just doesn't make any sense. We'll actually start talking about that once we get into, like, summations and stuff. But for now, let's just deal with this. So, we know that we are given these letters. So, all you have to do is just correspond each letter over to each thingy. This will always be the form. If you're missing your b, then plug in a 0 in place of the b. if you have a C, or if you don't have a C, sometimes that happens, just plug in a 0. Then it will be square root of b squared. And that's how it works. Here, let's do an example. Okay, so our b doesn't exist here. So we'd plug in 0, 0. So now we plug in our corresponding, what do we even call it? Numbers. So 1 goes into the A, because, well, it's an invisible 1. That's why I was talking about how it's transcendental. And there's a 1 for the C. So now it's the square root, here. So it's plus or minus the square root But wait a minute. We have an issue here. There is a negative square root. Negative number in the square root. Now, what do we do now? A while ago, with the Greeks, they had this issue with complex numbers, I believe, with finding the volume of a pyramid. And the thing is that, for the longest time, people did not believe that these quantities existed. Until they decided to just create an entire number system with it. Because for a while, I don't remember, it was some drunk guy who was gambling all the time that actually wrote a paper that led all the way up to this system. Because Euler went crazy with this stuff. You know, he basically sparked everything about this. After everyone kept rejecting it. Because, you know, it just shouldn't exist. If you do negative 2 times negative 2, you get positive 4. If you get 2 times 2, you get positive 4. The only way you would actually get a negative is if it was 2 times negative 2, but then that wouldn't be a square. And I believe this is what we call, what's inside the square root to be a square quantity. But this isn't a square quantity. So how do we deal with this? Here, let me erase this. I'm going to talk about the basics of a complex number, and then that'll be the end of the video. Because first of all, we need to understand how it works. So, if we have plus or minus the square root of negative 4 over 2, and we're dealing with x squared plus 1, I should probably keep that in mind, then all you have to do is just take out the 4. So plus or minus 2 root negative 1. Crap, I actually turned off my light. And you can cross these out, and now it's just plus or minus the square root of negative 1. And now we'll just do the basic notation that mathematicians use for imaginary numbers. That's just I being imaginary. I think it seems pretty easy. So it'd be plus or minus I. Although, how would I even exist? Because if you can't simplify it, then how do we know it exists? Well, let's do this idea. Let's start squaring it. Okay, here. Let me erase all of that. Because that's the solution to x squared plus 1. You can plug it in, but let me just talk about this idea. Alright. Oh. Quality fix. I don't understand that. Okay. Alright, so let's start treating this I'm not going to go too far with the graphs. I don't want to explain that until we get into like physics or complex analysis or complex variables. Probably just going to mix up complex variables and analysis, I'm not sure yet. I haven't gotten to decide yet because I want to move on to calculus and then I'm going to move on to different stuff. But also, I don't know what part it actually cut out or the quality started turning to crap, so I really apologize for that. I will be buying a new camera soon. I don't want that to happen. But let's treat this as the y-axis. And let's treat this as the x-axis. So this, if we were to graph it, would be a three-dimensional thing. It'd be like an invisible part of x. And complex numbers normally follow this, this format. Ignoring that x and y are different things, a complex number is composed of those components. So now, let's just talk about the squaring. So if you were to graph, let's say, x equals I, how would you do that? Well, this is treated as if it were a part of x. So if x equals I, then it would be a positive I right here. And we'll have this a negative I. 1, and then negative 1. Okay, so now we have our x my ear just went out. Hold up. Okay. So now let's square it. The square of the square root of negative 1. If you know anything about how radicals work, or just how exponential rules work, I'm going to write this in two different fashions. Just in case if you forgot. You know that if you multiply square roots, you get the number inside. So that would equal negative 1. And you know that if you add the exponents, you're still going to get negative 1. Because negative 1 to the 1 is still negative 1. So now our I squared goes to here. Let's just add another number to the exponent. So 2 plus 1. So what is negative 1, or the square root of negative 1 cubed? Well, let's see. You have the square root of negative 1 over here again. So now how do we deal with it? Well, you know that if you take these to be each other, then it's equal to negative 1. So multiply negative 1 by that, and you get negative I. So now we go over here. And then we add another exponent. By the way, you don't need to add all these together because you already have the solution to this part. You could separate them as long as the answers stay consistent. So now if you do it again to the fourth power, it goes to 1. You can do that by yourself, because negative 1 times negative 1 equals 1, obviously. Although, let's just look at this. It's going in a circle. If you keep doing those exponents, it goes in a circle. See, this is the thought process that Euler had when these came out. So he started combining. Actually, I believe this led to the famous Euler identity formula. Let's see, e to the I pi equals negative 1. Which was really, really quite the find. It's going to apply to physics, although I believe I said that in an earlier video. But let's just start talking about the properties of a complex number. Because think of it as in the invisible parts of an axis. Because we know that they exist, but they shouldn't exist, but they do. It's like how we give off radiation. It's a thing that we don't expect to have, and yet we have it. Because the universe doesn't bend to our will, we just follow whatever the universe says about itself. So let's just talk about this. If we were to have some arbitrary A, not the A from earlier, just this A. A can be any real number. So let's start factoring this out. I times I, that's just I squared. So you have -1. So you have AI right here, and you have another AI over here. So it's plus 2AI. And now you have A squared over here, so you pull that down. And we know that A is defined to be any real number. That is kind of a funky R. So since our i's just turn into real numbers, then let's just combine it real quick. So -1 plus A squared plus 2AI. Alright, and now let's fit it into the format of a complex number. So we defined it to be x plus iy. I'm not sure if that's in the video. Yes, it is. So now we have the components of x and y. So x would equal this, and y would equal the 2a. That's how this stuff works. Although, what about this? Let's say that this was just a negative. Here, I'm going to erase this. I'm still going to use that format. Okay. So you have I plus A times I minus A. So you, let's see, I squared, so that's -1. And then the AI's cancel, because that's how conjugates work. If you don't know what a conjugate is, if I remember correctly, I think I stated it somewhere, but it's just changing the signs and pretty much keeping the same format. Ugh. Sorry. Hiccups. Sorta. I don't know. And you know that the multiplication between these two will always cancel in a conjugate. So now we have -1 minus A squared. We defined A to be an element of all real numbers. I gotta stop erasing the good parts. So now let's put it into the format. We know that this is supposed to be real in the real plane. So where's our complex number? Our conjugates actually removed the complex part of this expression. So now we just don't have this, and we only have x equals -1 minus A squared. And we know that this isn't too complicated because it's just a real number. Let me think of what else to talk about. Aha! I almost forgot. Let's just start graphing our x. Well, let's just start with our x-axis. How do we graph that coordinate? Okay. So we have our I axis. Let's just put it in the same format. I'm not going to do it as a function yet. I'm going to wait for that. But for now, let's just start. I'm going to show you one example, and you should be able to do it straight away. It isn't too hard. So you have I plus 1. So our 1 goes here, and our I goes here. So if we treat it in ways, since this isn't on the real plane, so this can't be on this part. So it has to go upwards. But there's also a 1 that exists in this little equation right here. So that means it goes this way too. So it actually meets up right here. That's how it works. That's all you need to know about that. And soon we'll finally get into proofs. Actually, possibly, depending on how you guys react to me bringing in only pure mathematics proof-based thing. But I don't know what you guys think. Well, I believe that's all I have for today. And again, my apologies. I don't know what they're doing outside, but I'm not going to question it. So, let's see, what was I talking about? Whatever. Thank you for watching. Next week may or may not be the final video. I plan on getting the calculus playlist done as soon as possible. But that's it. Thank you for watching. God bless you. See you in the next video.